Hello there guys, and welcome back to another epic Inexorable maths video. In this video we're taking a look at the factor theorem, and we're just going to look at what it is and a couple of applications of it, but we're also in the future we're going to go into this topic with more detail. We're going to look at how we can apply it to polynomial long division, because that's the end goal here. The factor theorem is something that we'll learn about, but it's very, very important in relation to polynomial long division. So let's actually define what is the factor theorem. What does it say? What does it tell us? And this is what I've written here. So it says two things. The first thing is that let's say that we have some polynomial f of x. We should all be comfortable with what a polynomial is by now. A polynomial is simply some function. We're going to call it f of x. I'll just very briefly demonstrate what it is for you guys here, just to be really clear. And it can be any sort of thing. So let's say, I don't know, I'm just going to make one up. 5x minus 3x squared plus 100 x to the power of 65, something like that, right? That's a polynomial for you. Normally we like to write it in descending powers, so we would start with the 65, then the 2, then the 1, or whatever, but it doesn't actually matter. The only rule for a polynomial is that the number of terms have to be finite. You can't have an infinite number of terms because that's something else, that's a power series. And the other thing is that the powers of x must be natural numbers, so you can't have like an x to the half or something, because that is not a polynomial. Okay, so that's what a polynomial is. It can be anything. So quadratic is a polynomial, a cubic, and so on and so forth. And it says that for some polynomial, we're going to call it f of x because we don't know what order it is. We don't know if it's a linear function, a quadratic, a cubic, a quartic, a quintic, or anything else. We don't know what it is. It doesn't matter. So we're going to call it f of x. So when we let x equal p, where p is like some constant, if f of p is 0, then it means that x minus p is a factor of f of x. And it also works the other way around. So if x minus p is a factor of f of x, then f of p must be 0. So, why is this true? And also, maybe it's not clear what I mean exactly. Let's actually just really, very quickly over here, dive into sort of what's actually going on here. So let's say that we had a quadratic. I'll just make one up. Let's say we're going to go with, let's do a fairly simple one. Let's do x squared plus, what can we do? What about 7x plus 10? Okay, that's a nice little quadratic for us right there. And let's just do that. So then what we'll do is we'll factorize it. So we know how to factorize. So the reason why I chose this is because it's easily factorizable. We can get x plus 2, x plus 5. I hope that we agree that these two things are, they're equal to each other. I hope that we agree on that. So now, if we set it equal to 0, we can set both of them equal to 0. Well, what are the roots of this equation? Where is this equation true for what values of x? Well, x is equal to minus 2. And x is equal to minus 5, because if you substitute either of minus 2 or minus 5 into either two of these top equations, they are the same equation, just written differently. If you substitute into either one of them, either version, they're true when you substitute minus 2 or minus 5 in. Brilliant. So, why is that important? Well, what that tells us is, look at this thing. Look at it right here. We can say that if we call this function f of x, we'll say this is f of x, and we'll say this is f of x, they're the same thing, remember. And when it's not equal to 0 anymore, we'll say it's not equal to 0. Well, f of minus 2, well, we know what f of minus 2 is. It's 0, right? Substitute minus, we just did that, we just solved that. So we know f of minus 2 is 0. We also know that f of minus 5 is 0. These are the roots. So what does this tell us? Well, this is telling us that x plus 2 and x plus 5 are factors of f of x. And this is actually quite intuitive because, it's helpful as well. Look at this thing. For example, we can factorize x squared plus 7x plus 10 by just testing out numbers. So if we take this expression here and we just say try minus 2, okay, minus 2 squared plus 7 times minus 2 plus 10, and I'll move that down because my face is probably in the way. What is this equal to? Well, this is equal to positive 4 minus 14 plus 10, which is equal to 0. Because 4 minus 14 is minus 10. Minus 10 plus 10 is 0, so it's equal to 0. And we won't do it, but it's the same thing with minus 5. So what we get, essentially, is that, and you can see it, it's that we know that if we substitute in minus 2 here, we can then say, oh, x plus 2 is a factor of this function f of x. Same thing with if we substitute in minus 5. We know that x plus 5 must be a factor of f of x. So once again, let's just have a quick glance at what this says, solidify it in our minds. The factor theorem states that for a polynomial f of x, if f of p, so for example, in this question that we just did, or in this example, we chose p is minus 2, yeah? So f of, let's actually assign this a number, minus 2, is equal to 0. Then x minus, well, p was minus 2, so x minus 2, which is x plus 2, because minus minus is a plus, is a factor of f of x. And we know that that's definitely true. Look, in this example it is at least, x plus 2 is a factor of f of x, because we factorized it. And it turns out that this works for quadratics, cubics, quartics, quintics, and any other order of polynomial that you can think of. It works for all of them, and this is called the factor theorem. So why do we need to know about it? Well, let's have a little look at a question. Use the factor theorem to show that x minus 2 is a factor of x cubed plus x squared minus 4x minus 4. Okay, so you might say, okay, I know how to do this. I can use polynomial long division, because if I do x minus 2 divided by x cubed plus x squared minus 4x minus 4, I should get 0 as a remainder, because if x minus 2 truly is a factor of x cubed plus x squared minus 4x minus 4, then yes, the remainder should be 0. And that's true, you're right, that's definitely true, but the factor theorem is way faster, because the factor theorem just states that the only thing that you need to do to prove that x minus 2 is a factor of this cubic is simply substitute in, so we'll say that the cubic is going to be, it's x cubed plus x squared minus 4x minus 4. We substitute in the number 2, because we substitute in, remember, when we have x minus p, yeah, that if that is a factor, then f of p is a root. And this is basically what it's saying. So what we do is, right here, we have an x minus 2. So we're basically saying that in this question, p is 2. So all we need to do is substitute in p is 2, or, p is 2. You don't need to use p, but basically substitute in for f of p. So, f of x, just to be really clear, f of x is x cubed plus x squared minus 4x minus 4, which means that if we substitute in f of 2, then we get 2 cubed plus 2 squared minus 4 times 2 minus 4. Now, if, this is what factor theorem says, if x minus 2 is a factor, then this should equal 0. So let's see if it does. Well, 2 cubed, that's actually going to be 8. 2 squared is 4. Minus 4 times 2 is minus 8. And then we take away 4 there. So we have 8 plus 4. Okay, that's 12. Minus 8 minus 4. Oh, that is 0. Yes. So it is indeed 0. Which means that all we had to do, isn't that way faster than using polynomial long division? Way faster. That's all we have to do. We just need to show that when you substitute in your p value there, that's essentially, it's equal to 0. It's a root of the equation. So if x minus p is a factor, then f of p is a root. If x minus 2 is a factor, then f of 2 is a root. If x minus 10 is a factor, then f of 10 is a root. If x plus 1 is a factor, then f of minus 1 is a root, and so on. That is what the factor theorem states, okay? We will then look at, other applications of this in the future. But for now, thank you guys so much for watching. Highly appreciate it. And I'll see you in the next video. Cheers.